Hello, everyone. Thank you, everyone, for coming tonight. I'm Jan Knott. I am the Adult Programs Manager for the Haley Public Library, and I am really excited for tonight. In collaboration with the Idaho Dark Skies Alliance, the Sawtooth Botanical Garden, and the Boise State University in the back, and the astronomy lecture series, this will be our first one. We're going to have 3, and we are honored to host it at the Haley Public Library. So, as usual, if you can silence your phones, that would be wonderful. And there are 3 ways to watch this. You can any lecture at the Haley Public Library. It can be in person, it can be on YouTube streamed the night of, and it can be on our website later in the history, on our website in history for our YouTube channels. And I wanted to just announce the other 2 lectures for the Dark Skies Alliance. The second one is going to be on April 4th. It's Madeline McKenzie, and she will be talking about ancient relics of the Milky Way, and followed by stargazing again at the Sawtooth Botanical Garden. And then on June 25th, we were going to have Dr. Brian Jackson, and he will be speaking about aerial exploration of Mars. So now I'm going to have Leah Rogers come up, who is with AmeriCorps, and she is going to introduce Dr. Law. Thank you.
Okay, hello. Hello, everybody. My name is Leah. Our guest speaker, Dr. Charles Law, is a NASA Sagan Fellow at the University of Virginia. Dr. Law earned his PhD in astronomy and astrophysics. Louder. Okay. Dr. Law earned his PhD in astronomy and astrophysics at Harvard University, and utilizes facilities such as the James Webb Space Telescope and the Atacama Millimeter and Submillimeter Array, or ALMA, for his work. Tonight, he will be presenting on a revolution in planet formation, the ALMA era and beyond. We will deepen our knowledge and understanding of the universe before heading outdoors to experience the night sky firsthand at the Sawtooth Botanical Gardens. We will be playing this a little bit by ear, and we will announce by the end of the presentation whether or not we will be doing stargazing tonight. Weather looks a little bit hazy and cloudy, but we're hoping, keep your fingers crossed, that the weather will clear up. And this will be led by me, the AmeriCorps Night Sky Conservationist, Dr. Charles Law, as well as local astronomer Tim Frazier and our lovely AstroTac group in the back. It is with a great pleasure that I will welcome Dr. Charles Law.
All right, hello everybody, and thank you for that fantastic introduction. It really is my privilege to be here tonight and to get to share some really fantastic science, something that I really love. I'm going to tell you about how planets form and a revolution in our understanding of this process. Okay, to get started, here's the structure of my talk. First, I'm going to mention why we should care. Hopefully you already all care about planets. We are on one. You are here tonight. Hopefully I don't have to do that much convincing here. Then I will talk about the physics of actually making a planet. How do we think this process actually happens? And then I will link that to some observational evidence. And here I'll bring in some of the research that I do and some of those fantastic telescopes to really be able to learn about this process. And in the end, I'll look ahead to what I think is a very bright future for this field. Okay, so let's get started. So I first want to start with this image right here. And I think that this is just a very nice, oh, great, that's it, perfect. A very nice encapsulation for why we should care about planets. Because those little dots there, that's us. So this is an image from the Cassini spacecraft that actually turned back and looked at Earth. So we are there, that tiny little dot of light. You might see another dot of light there to the left. That's actually the moon. So we're really looking back at our own solar system here. We're all in that little pinprick of light here. And I hopefully don't have to convince you that why we need a planet, right? We need a planet to a place to live. We need a planet where we can actually have habitability to come about and be alive today. So I think this really underscores this. Also, there's another planetary phenomena in this image. You can see the presence of Saturn's rings here that are just sort of photobombing this image here. But what I want to convince you is that we live in a special time for studying planetary and astronomical sciences. And this is because two things are simultaneously happening. The first is we're getting these fantastic, detailed views of our own solar system. But at the same time, we are getting an ever-growing amount of data on exoplanets. So who has heard of an exoplanet before? Raise your hand if you've heard of an exoplanet. Okay. Yeah, great. About half of the folks. So for those that haven't, an exoplanet, as its name might suggest, it is a planet that is out there around a star that is not our sun. It is another world. It is another solar system that is out there. And we've begun to detect more and more of these and characterize them in detail at the same time as we're really investigating our solar system. So it's really two pieces of the puzzle here. And this wealth of data really gives us a ton of opportunities. So I'm just going to show you a little bit of the advances we made on both sides of both sides of the story here. So first, let's dive into our solar system. Why have we been able to make all of this advancement in understanding our solar system? It's thanks to the very fantastic fleet of missions that are being run by NASA. Here is just the subset that represent the planetary science feat. So all of these here are different missions, are different spacecraft, with very specific science goals. And whenever I look at an image like this, I'm just amazed by how many missions are out there doing all kinds of different science. The spirals right here correspond to what these spacecraft are studying. This is the moon and Mars at top, and the bottom is other solar system objects. I'm going to focus just on two of these to show you how transformative it is when you take a mission and you actually go and send it out there to one of these objects in our solar system, what kind of things we can learn. The first one is a mission called New Horizons, which perhaps you've heard of before. It was a mission to go fly by Pluto, so really to go to the outermost regions of our solar system. But before I show you the New Horizons image, I want to contextualize this, because even with our best space-based telescope, this is an image with the Hubble Space Telescope, a very famous, very large telescope, it looked at Pluto, and it sees a smudge. Right? You see maybe there's some color variations here and here and here, but this is a smudge, and this is still our best telescope. So there's no substitute for actually taking a spacecraft and having it come and fly by and get very close to Pluto, because when you do that, as what happened in July 2015, you get an image like this, a fantastic improvement. And what's more is you can then zoom in on this image, and you can look down to scales of tens of miles, or even in this case, that bar right there at the top is 6 miles. So really, you're seeing geological features, a large ice volcano, an icy cratered plain. You're basically able to see geology happening at this very remote world in our own solar system. So I just find this fantastic for what you can actually do when you send a mission out there. Sorry? No, these are just, yeah. So the mission actually went by and it flew by Pluto very, very quickly. It was going very fast, but it took a ton of images as it went. So these are images.
I was wondering if the volcanoes were alive.
Oh, that's a great question. They at least were active in the past. I'm not sure the sort of knowledge state in terms of understanding if they're actually happening right now. But these at least were active some point in the past. Yep. The other one that I wanted to show is a mission called NASA's OSIRIS-REx. And this is to go to an asteroid. And this is roughly to scale. So this is asteroid Bennu. It's about the size of the Empire State Building. And this mission was actually a sample return. So it wasn't to just go to this asteroid. It was actually go collect some stuff from the surface of this asteroid and bring it back to Earth for detailed study. And that's exactly what Bennu did, this mission did. It went to Bennu. Unfortunately, due to some PowerPoint issues, this is not a movie, but if you were to go online and Google sample return Bennu OSIRIS-REx, you'd actually be able to see a movie here where the claw is coming down, hitting the surface of the asteroid, and actually capturing some of that material. So it's just basically a giant claw, grabs some stuff, puts it inside of the spacecraft comes back to Earth. This happened in 2020. It took some time, but then it landed safely back on Earth in 2023. And there's been a long process about opening this up, distributing the samples to various labs throughout the world, and the analysis is currently underway. And so what NASA is able to do now, actually look at the composition of that asteroid's stuff. And they find that there's carbon, there's water, there's lots of interesting compounds in that asteroid's stuff. But I guess I would be remiss by not mentioning what the James Webb Space Telescope has done for planetary science. And this is James Webb. For those that have not seen it before, it is the largest space-based telescope that we have. It has a very characteristic shape. It has a giant sun shield that protects it from the sun. It has a large structure in terms of its mirrors that are all gold. That's actually covered in gold, so it reflects infrared light back better. It's the best infrared telescopes we have. It's meant really to go look at very far away things, galaxies, very, very far away. But it turns out we can also use it to look at our solar system bodies. This is a family portrait of images taken with the James Webb Space Telescope that show just really spectacular images of Jupiter, Saturn, Uranus, and Neptune here. And it gets even better. Here is a zoom in of one of those images here of Jupiter, where you can see all of this active planetary physics going on. You see the presence of moons. You see the presence of rings here. There is even aurora happening both in the south and the north of Jupiter here. So just really fantastic when you have this really fantastic telescope to go look. So much detail just really pops out. Okay, so that was just a whirlwind to the kind of detailed views we can get of our own planets and our own solar system. But at the same time that all this is happening, we are now detecting other worlds. Here is a portion of the sky that was observed by the Kepler mission. This is an exoplanet hunting telescope that NASA launched that is trying to find planets around other stars. The idea was that it stared at that patch of sky right there for a very long time. And what it was trying to do is basically see when a planet moved in front of the star, the total light you would receive would go down. You would see a tiny dip, then the planet would move away, and then the star would become bright again. So it was looking for these very tiny dimming events that would correspond to planets moving in front of their host stars. And when Kepler did this, instead of finding stars, right, it found planets. So each of the points there represent a detection of a planet around these other stars. The colors are corresponding to different sizes. So the blue ones here are Earth sizes, but Kepler also detected larger planets that looked like Neptune in orange, or even giant planets that looked like Jupiter in red. So a whole host of planets were detected. And from this mission, what we're able to say is that when you go out there and look at the night sky, what you should think is that essentially every star that you're looking at has at least one planet, perhaps more. So it is really a sea of stars, but also a sea of hidden planets. We can't actually see the planets with our eyes, but they are there. And this is just a general trend that has happened in the field. Here is the total number of exoplanets, of other worlds that we know about, as a function of their discovery year. So this is the cumulative amount. And what you can see is that, somewhat shockingly, only a few decades ago, we didn't know about any of these other worlds. But now, as you move a decade ago, this just peaks. This curve really, really rapidly expands. And now we have thousands and thousands and thousands. The colors here correspond to different detection methods, but that is not the thing I want to stress. I just want to stress the number of planets that we have. We are over now 6,000 confirmed other worlds out there. And if you just keep extrapolate this curve up, we're going to detect more and more and more with time. So it's a fantastic data set that we have now building about these other worlds. What's more is we don't just detect them. We don't just say, oh, there's a planet there, there's a planet there. We're able to, at least for a subset of them, understand something about their properties, how massive they are, where are they located. And that's what this plot is showing right here. This is the orbital period, so how long it takes for the exoplanet to go around its host star. For Earth, that is a year, so that's 365 days. The y-axis here is showing how massive the planet is. So if you go up to the top, those are very massive planets. You go to the bottom, those are very low mass planets. And what you can see here is when you compare these planets that we've discovered, these other worlds, to our own solar system bodies on this similar plot, they're quite different. They occupy an entirely different region of space, parameter space here, right? They're very different. Some of this is driven by biases in our detection techniques, but it still tells us that there's tons of planets that we've not since conceived of, right? Everything doesn't just look like the solar system. There's planets with tons of interesting, diverse properties that don't look like our own solar system. So exoplanets look different. You might ask how different, right? Maybe this plot doesn't really sort of show exactly how dramatically diverse some of these planets are. So I'm going to reframe this in a different way. And here I've basically, same plot, now I'm just color coding different regions that correspond to different broad classifications of planets. If you're here in the green region, all of these worlds, like this one exoplanet here, 55 Cancri E, is so hot that on the side that faces the star, you could melt iron. And so on this planet, you would have surfaces coated with flowing lava seas. An entirely different world than anything we see in our own solar system. If you move up into this blue region right here, such as this exoplanet, Gliese 1214b, you have something that looks maybe a few times larger than Earth, but based on our characterization, it looks like it's almost entirely covered in water, essentially a water world. And if you keep moving up and you enter this region right here in pink that is called hot Jupiters, this is WASP 18b, these are planets that are the size of Jupiter or larger, but they're going around their host star in a day or less. So they're absolutely whizzing around their host star. And again, we don't have anything that looks like this in our own solar system. And in fact, the discovery of these really shocked folks, that you could have a stable planet that is so large but is moving so very quickly around its host star. So one of the big takeaways from all of this is that if we are going to have a theory of planet formation, we can't just make our solar system. We need to actually be able to understand how all of these very diverse array of other worlds actually forms. Okay, so hopefully that's convinced you that you should care about planet formation, right? We have lots of interesting things that we're learning out there, other worlds, our own solar system. Let's now talk about how we think this process happens. How do we actually make a planet? And somewhat strikingly, the idea behind planet formation dates back hundreds of years to some very famous thinkers shown here, 1700s. And they put forth an idea that is quite strikingly similar to what actually happens in our modern picture. So here is in their language, this is from Laplace, what they said the process of making a planet is. They said this nebula, which they mean gas and dust, extending far beyond the orbit of the outermost planet, gradually contracted by its own gravitation, the angular rotary velocity necessarily increasing and the polar diameter diminishing as it contracted. Basically, that means gravity brings things together and you form a disk of material. By successive repetitions of this process, other rings eventually form the nearly spherical masses of the planets. And there, all they're saying is in this disk of material, planets are going to form. So translation of this is basically you have a cloud of gas and dust which collapses under its own gravity that forms a thin disk, and it's in that disk where you end up forming planets. So that's the idea. And that essentially matches what we think is actually happening. Now we have more details that we've filled in, of course, over the many hundreds of years. Here is the generic recipe for making a planet. And here you should look at this diagram here in a clockwise direction. You start at the top with a giant cloud of gas and dust. And certain regions within this cloud are slightly more dense than their neighbors. And because you have more stuff in these little regions in this cloud, they end up collapsing under their own gravity. So you have various clumps of material that are very dense and begin to collapse, and gravity just pulls them together tighter and tighter. So much so that at the center of this collapsing material you put enough material into a small enough region that it gets dense enough and hot enough to actually form the earliest phases of a star. We call those protostars, and they'll continue to take in more and more material as material falls onto them. They'll get bigger and brighter, and they'll eventually evolve into a fully fledged star given enough time. So in that process, though, you end up actually forming a disk of material. You go from this really chaotic, disordered state where all the material is falling in, kind of a mess, generally a spherical, swirling blob, to a flattened disk of material, because this is the most effective way to funnel material onto the central star. You need this to be able to conserve angular momentum. It's one of those fundamental physics laws. It turns out disks are the best way to do this. So in this process, eventually you'll end up with this disk of material, which in the same analogy to the protostar, we call a protoplanetary disk, because it is in these disks where we believe planets to form and acquire all of their properties. And given enough time, then we'll evolve to the end state here, and we'll have essentially a solar system. We'll have a fully fledged star, and we'll have a bunch of fully formed planets. So this is the generic process, which matches pretty well to those early ideas. And I particularly like studying this phase. This is the main area of my research, protoplanetary disks, because they represent that last stage where you have all of the material that ends up going into your planets. So the way to think about this is in the disk phase, you have an environment that's full of gas, that is full of dust. And that's going to actually make your planetary system. By the time you get to something that looks like our solar system, all of that dust, all of that gas is gone. And so if we want to understand something about how the planets get their properties, why they end up looking exactly like they are, all of the answers are hidden in this disk phase. Broadly, the story of planet formation is the story of dust, of very small dust grains. And when I say dust, you may think of the terrestrial dust, like cleaning, it's accumulating on your bookshelves. That's not exactly the dust that is present out there in interstellar space. These dust particles are very much smaller. Here, we're talking about things that are the size of a few microns. This image right here is of a dust particle of around 5 microns in size. If that doesn't mean too much to you, the comparison point is a human hair has the width of about 100 microns. So we're talking something that is many times smaller than that. So these are dust particles that are very small, not exactly analogies to the ones that we have in our everyday lives. But what's striking is that all of the planets, Earth, all of the planets that we see, really start with these smallest of particles and grow to end up being planetary size, which I find just absolutely amazing. Here is a rough roadmap for how you actually do this. Starting here in the upper left with those very smallest dust particles. And what ends up happening is they collide, they hit each other, they grow larger and larger, and they make their way along this plot here. They grow from very tiny dust to pebbles, something that's maybe a millimeter or a centimeter in size. And then those grow larger and larger to essentially miniature planets. We call them planetesimals. Some of these will end up as asteroids or as comets. Some of them will keep growing larger and larger to eventually form something that looks like the Earth. And if there's enough stuff available during this process, you'll end up forming something even larger, perhaps the whole way up to a Jupiter-sized planet. So what I want to do here is just walk through a few of these key phases for how we jump from the smallest of dust particles to the very large planetary systems. So the first stage I want to talk about is how do you go from those tiny, tiny dust particles to something like a pebble? It turns out this is the process that I'm going to be talking about, microns to millimeters. So again, this would have been a movie if the PowerPoint worked. So instead, I'm going to show you a few images from that actual movie. But it turns out for the very smallest particles, they just tend to stick together very efficiently. This is a computer simulation that some folks have run. This is one dust particle here. This is another dust particle here. And all they're doing in their simulation is they're having them collide with each other. And so what happens is when they collide, due to electrostatic forces, the material sticks together. And you end up with a particle at the end that is larger than those two dust particles that came together. Of course, this is not a perfectly efficient process. right, you can see that some material is ejected in this collision, but more of the material is bound together in these electrostatic attractions to make a larger dust particle. And so effectively, you can just have these things running into each other. They just hit each other, they coagulate, they get bigger and they get bigger, and this is an effective path to at least form something that looks like a pebble. So that's great. We can get to already, right, we're to a pebble size. But now, perhaps you've been wondering, how do you actually make a pebble into a planet? How do you actually take a rock and smash to a rock? Those things don't really want to stick together, right? They want to break apart, they want to fragment. How do you actually do this? And so this, for a long time, and depending on who you ask, an open question in our field. How do we actually go from these pebble-like objects the whole way up to a planet, or even an asteroid, really? How do we stick together these rocks? And so I'll just give to you two ideas for how this works. Folks sort of debate exactly when and how this process works, but I can give you two possible ways where you can stick together a bunch of these tiny rocks. The first is to use ice. If you look at your protoplanetary disk, right here, if you're in regions that are close to your central star, they're hotter, right? They're closer to the star, they're warmer. As you move further out in the disk, the temperature drops just because you're getting further away from your central star. And in this process, you end up crossing something called a frost line. The frost line is the location where the temperatures are now cold enough that instead of the gas being gas, it freezes and it becomes ice. And when it freezes, it tends to stick to the dust particles that are spread throughout the disk. So what that means is if you're trying to form a planet, if you do it in the outer regions where you're outside of this frost line, instead of sticking rocks together, what it means is that you're going to be trying to stick snowballs together, pebbles that are coated in icy material. And as you can imagine, it's much easier to stick snowballs together than it is to take just two bare rocks and collide them. So this presents at least one way to do this if you're forming your planet beyond these frost lines. One other suggestion that's out there for how to do this is to rely on the fact that the gas in your disk is not entirely smooth. Sometimes there's peaks in the gas pressure profile. And what that does, here I'm showing it in this, sort of orange-white region right here. This is a region you have a lot of local high pressure in your gas distribution. The dust is pretty well coupled to the gas. So if you have a lot of gas confined in a certain region, you will also confine a lot of dust particles in that very same small region. And if you're able to effectively do this, you can essentially have gravity just run away. You have enough material being packed into a tiny region because the dust is following the gas, and it's sitting there, and then gravity just takes over. And you can imagine sticking a bunch of stuff together via like a molten ball, right? Things are just really being compressed really quickly. So this is one other way to do this, to make a planet somewhat quickly. And it gets over the fact that instead of just taking two bare rocks and colliding them, you're just using gravity to really overwhelm them into forming to a bigger body. Okay, but we know this happens. Depending on exactly who you ask and what theory you're going with, we for sure know that we're on a planet, right? We had to go through this process right here. And the thing I just want to stress to you is, again, this is a trillion-fold increase in size from a micron to a planet. That's just fantastic to me. It's really hard to believe that from the smallest things we are all born. Okay, but there's one more step here, right? This is great if you want an Earth, but there are giant planets out there. There is Jupiter, there is Saturn, there is Neptune. What happens in making one of these very massive gas giant planets? So it turns out the key here is that you need to form your rocky core pretty quickly. Because what's going to happen is you have your large rocky core. Once it gets to a certain mass, it's able to essentially sweep up all of the surrounding gaseous material, as shown in this artistic rendition here. We have your rocky core that formed from the collision of those dust particles. And now it's basically sweeping up all of the gas that is nearby, and has a runaway process of accumulating all of that surrounding gas. This has to happen quickly because you actually want there to be still a large reservoir of gas out there to be incorporated into your planet. What's particularly interesting about this process, and I'll come back to it a little bit later, is that essentially you get a mini disk. You get a disk inside of a disk, because while you're making your giant planet, all of that gas that is swirling and accumulating onto the rocky core does so in the form of a disk, because it's the most efficient way to get tons of material onto that planet. And it's, in fact, in these miniature disks we expect there to be, in the very same analogy, moons forming. Tiny dust particles and this miniature disk coming together and making moons around these giant planets. So just keep this in mind later, because I'll show you another connection to this. Okay, and the last thing I want to mention is timescales. So for humans, maybe 1 million to 10 million years is a long time, right? Astronomically, that is quite quick. You can see this by comparing the timescale we expect for planet formation, which is on the order of 1 to 10 million years, to how long a star lives. So if you look here in this chart, for something that's around the mass of our sun, we expect that star to live around 10 billion years. For stars that are less massive than our own sun, they might live for hundreds or even thousands of billions of years. So that is all to say that stars that look like our own have fairly long lifetimes. And from their perspective, if you're a star, all this planet formation stuff is just happening in the blink of an eye. Very, very quickly, millions of years versus billions of years. Okay, so now I want to dive a bit into the structure of these disks, with an eye to connecting to some of the observations we're able to make. Here is a schematic cross-section of one of these disks. Here you're seeing the rough size. You'll see this term here, which is called AU. This is an astronomical unit, and 1 astronomical unit is the location of Earth with respect to the sun. It's how far the Earth is from the sun. So just keep that in mind here. In these disks, as you can see, you have the presence of a central star. All of the material is orbiting around that central star. You have a region in the disk where your planets are forming. This is where all the material, once it gets bigger and larger, it ends up settling down into this relatively flat region. And that's where you can have all these collisions for planets to grow larger and larger. And then in the center, we also expect some of this material to be going into the star. So essentially, there's a competing process. Some of the material in the disk is going into the star. Some of the material is going into the planets. And in this process, they're both sweeping up the material. And that's why it only lasts for a few million years, because everything is trying to get rid of all that stuff. It's either going into the planets, going into the star. And so give that enough time, and you're not going to have any stuff left over. Okay, so there are folks that study each portion of this disk here. You can see labeled there's a location for hot gas, for cold gas, for small dust, for large dust. There are folks that unravel these disks and try to understand the exact distribution of all of these different components. And they all play an important role in shaping how planets are forming. But today I just want to talk to you about, for the rest of this talk, this population here, the large dust grains. These are things that are the pebbles that I was talking about, a centimeter or a millimeter in size. They are the particles that are now sufficiently large that they've settled into this midplane here, and they are the raw materials going into planets. So when I say large dust, really just think about that is the reservoir for making planets. These are the particles that are going to collide and grow larger and larger. So that brings me to how do we know, right? This is a very nice story that I told you about how and where planets are actually coming from, but how do we know any of this is true? The first discovery of these disks around stars were quite a surprise. So if you look just at a star with your telescope and you measure how much light you have as a function of wavelength, that's what this curve right here is, you get a very characteristic shape. This is called a black body curve. It's set by the temperature of your star. So essentially, if you just tell me the temperature of the star, I can draw you that curve. So that's great. That's exactly what we'd expect. We go look at a star, we get a curve that looks like that. Great. What happened was that folks were looking at very young stars. And they were getting something that looked like that yellow curve, the one that's labeled extra emission here. They were seeing a star, but they were seeing a component at longer wavelengths where they had excess emission. And what they were able to find was that this actually was due to the presence of one of these disks surrounding the star. there was extra light coming from the disk that was essentially contaminating their observations and causing this difference in the shape of these two curves. And so it was from this method that folks were able to first detect the presence of these protoplanetary disks. And again, here's just another way to look at that. The yellow here would be the star component, and the red portion here would be the disk component. And for every observation that picked up a disk component, you would say, yes, oh, we've detected one. And here's some real data that actually shows that. Each point here is a measurement. If you just had a star, you would have this great curve. But you have points here, 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 going further out, which means this difference really is the fact that you have a disk here that's contributing extra light at these particular wavelengths. So this is great. This is a great technique. It allowed for hundreds of disks to be detected. But it is really a binary. It is, yes, we see a disk. No, we do not see a disk. We don't actually get any spatial information about what those disks look like. And it's only within the last 20 years or so, particularly within the last 10, have we been able to use some new techniques to map out the spatial distribution of these disks in detail. And we're doing this in two ways. We're using something called an interferometer, and we're observing at millimeter wavelength light. So I will walk through what each of those means and why they're important. First, let's talk about millimeter wavelength light. If you go out with your optical telescope, looking at visible light like what we see with our eyes, and you look at one of these giant clouds out there in space, this is the Taurus cloud, this is what you might see. If you notice here that there's a background of stars, but along this region right here, this arc, you don't see stars. There's a diffuse, nebulous blackness that extends throughout the image here. What this is actually the dust particles in this cloud absorbing stellar light. And so you're not able to see through it. You're not able to see the stars on the other side. But if you look at this very same cloud, but you had millimeter eyes, this is what you would see. The same structure, stars are gone, but now you see just the dust particles. And why is this happening? It's because with respect to background space, which is very, very cold, these dust particles have a tiny bit more energy. They're a tiny bit hotter. I hesitate to say hot because these things are around 20 Kelvin, more than negative 400 degrees Fahrenheit. So still very cold, but not as cold as the background of space, which means essentially that they are glowing with respect to millimeter wavelengths. If you had a millimeter wavelength eyes, you would be able to see the glowing dust. So this is a technique that we can use. If we build a telescope that can have these millimeter eyes, we can directly see the structure of this dust. Because it's nicer to work with the image on the right here than necessarily the image on the left. You can see the dust directly. And it's the same dust that we expect to be present in the disks themselves. So just on a smaller scale, in the disks you have that same population of dust that's going to be hotter, that's going to be emitting. So we can actually use this very same technique to make images of the actual dust in these protoplanetary disks. But there's one issue here, which is they are quite small. If you think of the scale of our solar system, we're talking 50 to 100 astronomical units. If you look here, this cloud is tens of light years, hundreds and hundreds of thousands of astronomical units, which means we need to build a big telescope because our formula for our resolution, so how carefully we can separate two things on the sky, depends on the wavelength. That's what the lambda is right here. And we're stuck in the millimeter, so we can't change that. But it also depends inversely on the diameter of your telescope here. So if you build a bigger telescope, you get a better resolution. So larger telescopes, better resolution. These disks, again, just to compare, they're a few hundred AU. This thing, hundreds of thousands of AU. So let's try to build a big telescope. Let's plug in these numbers and see what happens. Let's build a giant telescope in the radio that can see these millimeter light. Here's one in Spain. Here's one in West Virginia. These are monstrous telescopes. The one in Spain is 30 meters. The one in Green Bank, West Virginia is 100 meters, a single dish. So fantastic. If you ever get a chance to go to West Virginia, you should definitely go see this telescope. It's actively used today. You can do tours. But what this means, if you plug in those numbers, the resolution that you would achieve is still much greater than a typical disk. It is over 1,000 astronomical units, or over several hundred astronomical units. And you remember, the disks are about 100. So these are just not good enough. We're not able to actually see the disks themselves. So what do we do? This brings me to one of my favorite telescopes that I use quite a lot, and I think is just a marvel. It is called the Atacama Large Millimeter Array, or ALMA. And you can see that in the name there's the word array, because what this is something called a radio interferometer. What that means is that you're actually linking up multiple telescopes together to work together as a super telescope. And so instead of just having to build one giant monolithic telescope, you build multiple dishes that you then have operating together looking at the same objects. In the case of the ALMA array, it is 66 different antennas all working together. So it's a huge telescope. Each one of these is around 12 meters in size, too. So they're pretty massive. They're not small, and we have 66 of them.
Are they all in one place?
I will get to that. They are not. So it's in the Atacama Desert, hence the first part of its name. It's located right there at the northern tip of Chile. And it's located in a very high and dry plateau, over 16,000 feet. Here is the ALMA site, you can see. We want to do this because it turns out that water vapor in our own atmosphere tends to absorb these radio wavelength light. And so if we put the telescope somewhere very high, without a lot of water vapor, the Atacama Desert is perfect for this, it really improves our observations. So there was a question about, are they always in the same place? And they are not. Here you can see one of those telescopes on top of a giant truck that actually drives them around. So this is not a static array. You can pick up and you can move these dishes as much as you want. They're huge. I mean, look how many wheels that truck has. And you can actually see, this in detail. Here's just a small portion of the array. Do you notice there are small triangular dots throughout this image here? These are actually the pads for the antennas. So what the array did is they built out hundreds and hundreds of these pads. And you can pick up the telescope and then drop them on whatever pad you want. So essentially, it is fully reconfigurable. And how this works in practice is that it has around 10 nominal configurations. And all throughout the year, they're constantly picking up and moving these telescopes throughout these different configurations, because there's a science return for doing this if you observe something in one configuration versus another configuration. The thing I want to stress is that you can take two telescopes here, and you can move them as far apart as 10 miles. And that really is the key, because now you have a telescope that is the size of 10 miles without having to build a single dish that is 10 miles, and that's impossible to do, but it's relatively easy to pick up one of these dishes and move it 10 miles away. What that means is when they're working together at these 10-mile separations, now you have a resolution that is better than an astronomical unit. You can make images of these protoplanetary disks at a resolution that is smaller than the distance of the Earth to the sun. And I think the best way to really illustrate what this has meant for understanding these disks is to show a before and after. Here is an image in the pre-ALMA days of one such protoplanetary disk. This is, again, showing that large dust, glowing dust. You can tell, yes, there is dust there. It's bright. But you essentially see no structure, right? You just see a blob. When ALMA came online and looked at the very same disk, this is what you see. It's an incredible improvement. All of those rings and gaps are real. This is a real image that came from the ALMA telescope 10 years ago. And so this was one of the first times that ALMA actually turned its millimeter eyes and looked at one of these disks and just blew us all away. And in fact, sorry?
What makes that red? Is that artificial or
So the red itself is just a color choice. You have to pick. So the question was why is it red? You just have to pick a color for this. So you could be blue or red. You can pick whatever you want. The important part is the intensity distribution, right? The fact that it's brighter here, here, and here, and then you have these dark lanes throughout. Is telling you that there's an absence of dust, right? There's actually a region that has been carved out, perhaps by a planet. And in fact, there's an even better one recently, an even smoother one. But what I want to just highlight is we're really getting down to the scales that are relevant to our own solar system. Here is what happens if we plot the location of the orbit of Uranus in green and Neptune in blue. They are really, this is something we can directly probe. What's more is that if you go back, so I wasn't actually able to show this movie, again, because of PowerPoints, but there was a very nice sort of artistic rendition which showed basically that if you have these planets, they're going to carve out these nice rings and gaps. And this whole movie and artistic rendition was made well before all of these ALMA images. And I just find it particularly striking is that the sort of idea that we all had about these rings and gaps actually matches very well to what we're seeing now. Because if you imagine a planet forming in this disk, it's going to be orbiting around, growing larger and larger and larger, but that means all of the stuff in its way, it's just going to accumulate. And so as it's, say if there's a planet located in here, as it's orbiting around, it's sweeping up that material. And so that's exactly the reason that there maybe is an absence of dust, that you have a planet carving that out. But it isn't just this one disk. It turns out this wasn't necessarily just a special source. Pretty much every disk we look at with ALMA at high resolution, we see these structures. We see plentiful rings and gaps. I mean, some of these are really fantastic. 7 different rings and gaps in this system. It's incredible. And again, to really drive that point home, this is small scale stuff. That bar right there is around twice the size of our solar system. So really, we are looking at other worlds that are comparable to our own solar system. What is fantastic about making images like this, besides them being really beautiful, is that what you can do is infer indirectly the planets that you would need to make those structures, to carve out those gaps. So here is a plot from one of the papers that actually came along with these images, where every point here in orange is an exoplanet, planet in these disks that's actively forming, that you would need to reproduce all of those structures that you saw in the previous ones. So you can do it with this population of planets. You can go to those images. You can say, oh, exactly what planet do I need? How massive does it have to be? And the answer to that question is all of those orange things right there. So if you have all those orange planets, that can reproduce all of those observations that we saw. And it's very complementary to these other detection methods. We can see planets that are hard to detect via other techniques. But one thing that has come out of this in more recent years is exactly how many. I think everybody within the community agrees that there are planets forming in these disks, and that they are the reason for these structures, the fact that these disks are not just entirely smooth. But when we looked at it in more detail, we realized that one could build a model where every single gap that you see here is being carved out by a planet. So in this one system here, you might have 3 medium-sized planets carving out each one of these gaps. But then folks also realized that you could do it with one planet. It turns out if you have one particularly massive planet, it can globally distort the disk and essentially trigger a wave of pressure distortions that will end up producing all of the other features. So you can't necessarily always assume every gap is equal to one planet. So that naturally begs the question is, can we do better? Can we use ALMA to be able to directly image a forming planet, to know unequivocally that, yes, there's one forming and where it is in the disk? And it turns out the answer is yes. And this is very recent. This is not something we've been able to roll out to many, many sources yet. But yes, we can. Here's one of these protoplanetary disks. The colors here, again, are corresponding to the dust distribution. So you have a very broad ring of dust, interior to which you have this giant cavity. That is, you don't have a lot of dust in the central region. And what has actually happened is that there are 2 planets in this system which have carved out that giant cavity of dust. And in a very high resolution image with ALMA, what you can actually see is 2 blobs of emission, where you just have a tiny bit of dust at the locations of these 2 planets. One there at the top, PDS-70C. One at the bottom is PDS-70b. PDS-70 is just the name from the catalog of this star. The name doesn't matter so much. But the fact that you can see dust swirling around 2 very young planets is particularly striking. And I just want to show you, here's the architecture of this system. So the observations are here on the left, and here is sort of a schematic view. So planet 1 is at around 22 astronomical units. Planet 2 is at around 34. So these are pretty giant planets, pretty far out from their stars. But if we look at one, if we look at this one in particular, the one that's a bit brighter, here is, again, a real image, one of the highest quality images we've ever taken, zoomed in at the location. What you see here is a bright blob, but do you notice this nebulous, fuzzy material surrounding the planet itself? Doesn't that look something like our initial artist rendition for a tiny, miniature disk in which moons are forming around this young planet? Of course, we'll never be able to see moons, tiny moons in these other systems. But the fact that we can actually see this very small miniature disk around a planet matches very well to the predictions that we would expect. And so what we really believe that we're seeing here is one of these moon-forming disks. And it's a direct image, which I just find fantastic. And if we just go back and think about our population of exoplanets, now we have added one more technique to be able to detect these planets. We can detect planets now in disks. And of course, it's a new technique. We've just added a tiny sliver to the new detections, but I expect in the next few years, really, we'll be able to detect more and more of these youngest population of forming planets. Okay, so in my very last few minutes, I just want to look ahead a bit to the future and show you about what is coming next. So the thing I want to talk about really is the fact that the material that is closest to the central star, right here, turns out ALMA can actually not see that. The gas is too hot. It actually doesn't emit in the millimeter wavelengths that I've been talking so much about. It actually emits in the infrared. And so very much an analogy, if you ever walk in front of one of those like body scanners where you see your heat signature, that's in the infrared. And that's the sort of temperatures we're talking about in here. And so you can only actually see these in the infrared. But this matters a lot because this is the region where we think terrestrial planets or Earth-like planets are forming. So if we really want to get at the conditions of the Earth-like analogs really close in, we need an infrared facility. But it turns out, thankfully, we have one now. That is, the James Webb Space Telescope is meant to be the world-class premier infrared facility. And with JWST, we're unlocking entirely new windows on these systems. So this is the same system I showed you before where you had the 2 planet detections. But it turns out when folks looked at this with James Webb Space Telescope, they were able to look in the centermost region right here, where maybe you're forming an Earth-like planet. In that region, they detected water. This spectra right here is essentially the fingerprints of emission from water vapor. Every one of these peaks outlined in blue is one of those fingerprints. And so what this means is now with the James Webb Space Telescope, what it's telling us is that in areas where we expect Earth-like planets to form, there is plentiful water. This is an important molecule that we really need for life, for our oceans, and the fact that we're now actually able to see that water out in other systems is really powerful. What's more is that JWST, because it's so absolutely sensitive, it has been able to detect the presence of fairly complex organic molecules around these other worlds. And in fact, because the James Webb Space Telescope is sensitive to those regions where we're forming Earth-like planets, the fact that in those same regions we're seeing complex molecules, this is an aromatic ring, this is benzene, the fact that we have complex molecules in the same locations where we're potentially forming Earth-like planets really is starting to point us to the fact that we really might have life-important molecules out there. We might have the chemical reservoirs that we need later on to eventually form prebiotic molecules, to eventually form life of some sort in these other systems. And so with a facility like this, we can really get at some of those really big picture questions about how did we come to be, and are we alone? But with that, I will just wrap up now and say the real story of planet formation is happening in these so-called protoplanetary disks, where planets are forming out of all of the gas and dust that's left over from the star formation process. We're using facilities like ALMA to take these absolutely spectacular images of ongoing planet formation. And in some cases, we can see those planets directly. And now with JWST, we're opening up this whole new window in studying these systems. And really together with ALMA and with JWST, we have already revolutionized our view of how these systems are forming. But I really think that going forward, the future is quite bright, and we're going to be able to answer some of these very fundamental questions about our own cosmic origins in the near future. So thank you very much, and I'm happy to take any questions.
Does anyone have any questions?
What's the lifespan of that?
I think we have one right here.
Sorry?
Astronomical unit, 93 million miles.
That sounds right. Well, the question was, what is an astronomical unit? That sounds right, 93 million miles. I don't actually know the conversion off the top of my head. It's quite far.
You describe the size of objects being multiple astronomical units. Probably 200, 300 million miles.
Oh, yes, absolutely, these things. Miles start to not, the question was when you're describing things that are multiple astronomical units, what is that in miles? And miles becomes less helpful because the numbers get so big, hundreds of millions of miles and things like that, yes. The astronomers have developed their whole other system for distances that sort of uncouple themselves from miles because the base unit is just larger and larger. So the one unit is a parsec, for instance, which is around 3 light years. And people will use parsecs and then say things like kiloparsecs or megaparsecs, so the 10 to the 6, 10 to the 3, just gigantic, unimaginable distances from our human brains.
Okay, I'm curious about something. I'm looking at this and they're all this dust is going around this central point, but the ones that are further out are going faster than the ones that are in the center.
So the question was, looking at these systems, what is the rotation of the material? And so in these systems, essentially all of the rotation speeds is set by the mass of the central star. All of the mass in the system, 99% of it is in the star. And so all that matters then is the mass of the star and the location of the object that's rotating around. And then it's basically Kepler's law applied to that system. You put in the mass of the central star, you put the location of your object, and that tells you how fast things are going around.
Well, my question was, I was thinking that looking at our solar system, that the smaller planets are inside and then they get big and then they kind of go like this. So if each of those lines is a different planet, would each of those have a different configuration of chemicals?
Yeah, okay, so the question was, like in analogy to our own solar system, how we have distribution of small planets, then larger planets, then sort of small again. Would you see something similar in these disks? And broadly, yes. And in fact, if you look at the sort of big, sorry, I'm going to scroll back a bit, sorry for doing this. You can see that kind of here, right? If you say, let's forget what I said about the caveats and just place a planet in each one of these gaps, the architectures are hugely different amongst this sample of systems. And so you would expect maybe some of those look like the solar system, but some of them are going to be entirely different from ours. So you could sort of get a whole host of different structures in these. So I think that there's a lot of diversity in these systems that we're already seeing.
Let's go in the front and then we'll go in the back.
I seem to recall that the speed of light was 196,000 miles per second. Is there anything that in your work today that you see that moves faster than that?
The question was, does anything move faster than the speed of light? Do we have evidence of that? And no, we don't. That seems to be the universal constant for the speed of, fastest speed that is possibly attained. So, no. Which is good, because a lot of our fundamental theories, rely on that. So, it's hanging together.
In the back here.
This is going to sound so dumb. What makes gravity become that?
Yeah, great question. So the question was, what is gravity? How does gravity work in these systems? What is gravity? That I do not know. That is a philosophical question. I do not know what is gravity. I mean, beyond it being a fundamental force that operates, right, in our universe, right? We know, we can see its effect. And essentially all that it is masses attracting each other, right? If an object, if a particle has mass, and another one also has mass, their amount of gravitational attraction will depend on the mass of those two particles. And so in all of this case that I'm talking about here, all of this dust, all of this gas, all of these stars have mass, and they will pull things together. It's a mutually attractive force. I mean, even here on Earth, right? The reason we're not flying off and standing here right now is things are pulling us down. The Earth is much more massive than us. We have a little bit of mass, and so we're very much attracted to the Earth. Sorry? The curvature of space-time at these scales, not important. We're close by. You mean like in a cosmological sense, or do you mean just like gravity distorting things? Oh, yes, okay. I mean, that is sort of the mechanism for doing this, why the forces are mutually attractive. The modern idea here is that it actually causes curvature in space-time, and that things will be attracted. Yes.
There's one back here with
Does the presence of multiple stars in these systems, like without a code, you still get a photoplanetary disk, or does that like affect it in any sort of way?
Yes, so that's a great question, which was what happens when you have a multiple star system, a binary or more? And it depends. If they are very close together, you can still have a disk around, and the disk doesn't really care about the binary nature. If you have two stars that are a little further separated and they each have their own disks, then yes, it will just, you won't have a nice, nice circle here. Things will be quite distorted as materials running into each other. So binarity, multiplicity, how many stars you have, all of that could very much mess up these disks. And I would say that even within the community now, within research, there has been a bias towards focusing on single systems for this exact reason, because single systems are nice and orderly, and people don't want to necessarily handle the binaries. But it matters because, especially as you go to higher mass stars, you'd more than likely not expect there to be another star. Right? The binary fraction of a higher mass star is quite high. You have a lot of multiple systems. So we have to do it. We just haven't done it yet.
Okay.
Any other questions? Yes.
When ALMA, that you can move those disks and make basically a huge disk by integrating the signal, well, couldn't you do the same thing with the VLA?
Yes, that's exactly how the VLA works.
I know they do that, but can't you use that for the same kind of research?
Yes, so the question was, is ALMA necessarily unique in the ability to reconfigure its array? Why not do something similar with a very large array, which is a centimeter facility in New Mexico? And yes, the VLA is reconfigurable, has 4 different configurations, and it is used to observe protoplanetary disks at centimeter wavelengths. So we have images of like this with the very large array. It's slightly less sensitive, just based on the number. Yes. It's probing, I mean, it is slightly less sensitive, but it is useful because it's probing something slightly complementary. The wavelength you look at in terms of these dust particles is roughly proportional to their size. So the millimeter observations give you millimeter dust grains. The centimeter observations give you the centimeter dust grains. So they're a more evolved population. And so the idea is you do actually want both views. It is very hard to make an image like this with the very large array. Making an image like this would take you probably 70 to 80 hours, whereas with ALMA it takes you 30 minutes. But there is an upgrade coming. There's a next generation VLA in 10 years. It's coming. So, sorry? Very, very large array, uncreative names.
What country is in charge of when you move and how you move this equipment?
Yes, so the question was what country is in charge of reconfiguring ALMA? But I guess broadly, what country is in charge of ALMA? And no single country. It is an international consortium which has representatives in Chile. There's a North American part, there's an East Asia part, and there's a European part, all of which have roughly equal contribution in terms of the financial decisions and operational decisions. In terms of actually setting the array configuration, that was something that was agreed very early on, and even before they actually built the telescope. And so they knew that they would be cycling through these various configurations. So that was already sort of set ahead of time and designed to be able to do that. But all of these partner institutions make the decisions together.
So can you explain why scientists can cooperate like this and the rest of us can't?
I cannot.
What's in the makeup of the scientists? Is it that you have some other goal in mind that you want to do now?
Curiosity, right?
Yeah, so the question was the cooperation. Why are scientists more perhaps uniquely able to cooperate in ways that other sectors of society are not? It is perhaps that. It's perhaps that sense of natural curiosity, exploration, unified goals, right, trying to understand the universe.
Pretty amazing.
But yeah, they get along okay.
Let's do, if there's one more question, we'll make it the last one. And if not, we'll end. Yeah, up there, yep, in the back.
I'm going to ask more about the ALMA array. Perhaps you don't know the answer, but what was into coordinating them as well as like some of the underlying infrastructure to support that massive?
Yeah, so that's a great question. It was basically logistics for supporting ALMA. How does it actually work? And I guess there's two answers there. I mean, one of them is just it's expensive. You have to run electricity up there. You have to run all your signal processing equipment up there. It is an interferometer, so what it's actually doing is it's making a measurement for every baseline of antennas. So it's basically, think of pairs. Every possible pair of the antenna are making a measurement all at once. So you can imagine the data volumes. All of that gets fed into a giant supercomputer, which is called a correlator, which calculates all of these measurements. And then that eventually sends it down to like the nearby town after it's done all of those calculations. And so there's multiple steps. And then people pick up, and there's like a data center in Santiago, Chile, that handles more of the process data. And then they actually send it out to their representative data centers in North America and Europe and East Asia. So it's this distributed thing that goes from the telescope sort of the whole way down and gets out to the world then. All right, thank you very much.
Before you guys go, we're going to just make an announcement, which is not up to me, if there's going to be stargazing after this. There is going to be.
Okay, so unfortunately, stargazing will be canceled for tonight. It is looking a little bit too hazy for us to be able to focus our telescopes on anything, but this will be a little bit of an incentive to come to next month. So hopefully, keep your fingers crossed, and next month, hopefully, we'll have clear skies and we can go out there. But yeah, thank you guys so much for coming out and seeing our talk. Have a great night.
Thank you.